will be minus infinity if a greater than 0. It will be 0 if a equal to 0, and it will be plus infinity if a less than 0. Correct. So 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 yeah, I mean something like infinity into 0 is 0, right? I mean this is fine. I mean like here we have defined it as infinity into 0 is 0, and it says that that uh, mm, this is well defined. There is no problem. Okay. Now 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 what about this infinity plus infinity? What is that?
Infinity.
Minus infinity minus infinity
Infinity.
or
Minus
minus?
infinity. Minus infinity.
Yeah. And what about infinity minus infinity?
Infinity. In,
What is this?
so it is indeterminate term.
Yeah, so this is basically not defined. Okay. So this is not defined. This is not defined. So these are certain conventions we keep in mind whenever we we go around it. Okay. And uh, so okay. Now Now, uh, I can do certain things. I can I consider real number. I consider R. So that was from where we went to the thing. So R. Now, now what we have seen that we can define the length of an interval, right? R is uncountable, but I can always define the length of an interval. Now, now what about so if I consider all possible intervals of the form so that means I mean I can yeah, I can have not only this I can also have okay they just we can have like this also. So this is so all possible intervals over. Hello.
Yes, sir.
So was it disconnected in meantime? Hello.
Yes, sir.
Was it disconnected for a little bit time?
Yes, sir. Yes, sir.
Can you see the notes now? Now or you cannot?
No, sir. We can not see.
Okay. Okay. So what we are doing is we are considering R and all possible intervals over R. And yeah, I wanted to do this thing. So And okay, so yeah, so if I define uh, like this, and and uh, and even I can have the in collections like like so I have like this uh, you know, because all these are intervals, right? I mean, these are all intervals. You can have, and similarly, I can have a, I mean, any interval will be any of the this following form, right? I mean, be but if you consider any interval, I mean, you consider you, but I wanted to tell that you consider R and all possible intervals over R. Consider R and consider the all possible intervals over R. And and so 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 the, I'm trying to give this example because if you have R, and if you consider all possible intervals over R, I mean, in a sense that, mm, so for example, in this example, we have started here is you have A, B, C, right? And you consider all possible subsets of A, B, C. And this forms a sigma algebra. And here I am telling that you consider R and consider the all possible subsets of R. And this is denoted by Borel of R. So, so I consider the sigma field or sigma algebra as the all possible intervals over R. So uh, uh, you have R, and I consider all the possible these things over R. That will give me the this thing. I mean that will actually this is the sigma algebra over R. The all possible subsets. I mean all possible intervals over. This is given. This is the uh, sigma algebra over R. And uh, so yeah, I mean, and this is called the Borel sigma algebra. Okay? This is called the Borel sigma algebra. Borel sigma, and uh, and and any set or so what are the B of R? I mean, so in a sense, what we are doing initially, you have omega, and you are considering the sigma algebra over omega, which is F. And for real line R, you have BR. The set of all possible. I mean, you can consider all open subsets of R that forms a sigma algebra. You can have, so this is the open subsets of R that forms a sigma algebra. You have this type of thing. This also, you consider set of all possible this type of intervals. That's also Borel sigma algebra over R. And and any element of this thing, because if you consider any subset of R, it will be one of this format, right? It will be one of this form, uh, and uh, and uh, and these are called Borel sets. I mean, any element which is here is called the Borel sets. Any element which is here is called the Borel sets. And and this is important. This is important because so for example, mm, if I consider this thing, if I suppose I consider this thing, I mean, I consider a sigma algebra. I consider a sigma algebra. That sigma algebra. So sigma algebra generated by this type of interval. Okay. If I can consider this Borel sigma algebra, so you see, this will be a sigma algebra. There is no. So, for example, uh, there is a mistake I have done. That is, I have to, but here I will consider with the equality. So with the equality. So I will consider it. Now, because you see, I mean, if you consider any interval over this, okay, suppose CD, you consider. What is the complement of CD? Anyone over R?
So minus infinity to C closed.
Yeah, minus infinity to C closed
U-
union
Union
D
open D
to
to plus infinity.
yeah. So
At infinity open, sir.
sorry.
At infinity open bracket, sir. Open D to open infinity.
Okay, you can take the close one. That is also, yeah. I mean, because here I have considered the equality. So in a sense that yeah,
Okay, sir.
yeah, so it's okay. I mean, this minus infinity plus infinity, those are a little bit tricky. Let's keep it. That's not the case. What I am trying to convey is that this is also an interval over R, right? Interval over R. This is also an interval over R, right? This is also an
Yes,
interval.
sir.
So yeah, this is also an interval. Uh, so for example, if I consider something um, singleton set, A, right? Uh, so is it a Borel set? Is it a Borel set? So how we define the sigma algebra like this, right? This way, like this type of interval. So in a sense that anything is part of the BR, we can call it a Borel set, right? Borel sets are nothing is the elements of the Borel sigma algebra. So in a sense that I have to express A in terms of this type of interval, and I can do it like this, right? I mean, if you just say n belongs to natural number, if you just write A and so, so you can write it that A minus 1 by n. Sorry. A. I can write it A minus 1 by n. And I take the countable intersection of this whole thing. So any singleton set, I can write it like that. It's like that. And these elements are Borel set because this is part of the sigma algebra. This open closed thing, right? So each of them is in the Borel sigma algebra, and this is the countable union. Uh, so this is also the countable union is also part of the sigma algebra, Borel sigma algebra. So therefore, this is a Borel set, right? Because this is the countable intersection of Borel set. So this is nothing but the countable intersection of Borel's countable intersection. Therefore, this is also. Similarly, what about this interval? If I take like this, I I defined Borel sigma algebra as this, and then I am saying these examples. Okay, I can look at the I can define the Borel sigma algebra also the uh, collection of this, and there is no issue. Then I have to express the things in that. So now you tell me, what about this interval? What about this? So I have to express something as the countable union of so AB. I can write it as N. I can always write it like this, right? Be my so it is going it is going to the B. And this is also countable union of Borel sets. So therefore, this is a Borel set. Similarly, suppose I define this, I define this as the open interval. Suppose I define like this type of, and then what about uh, is this a Borel set? Is this a Borel set? Sorry. Is this a Borel set? Now, how can I express this one? I can express this one as how can I write this? So this one I can write it as can I write it like this? Can I write it?
No, sir.
Huh?
No, sir. Then how A will come if
So this is A, this is B, right? So A minus 1, A minus, so this is A minus 1. Then you will have A minus half. You will have A minus third. So like this, it will close it like this, right? But it will always keep the A, right? Isn't it?
yes, sir, yes, sir.
So this way you are closing in, you are closing in, you are closing in, and then but it is A minus 1 by n. So as much as you can go, you close it in, but it will keep A. So okay, correct. Also, you can look at it like this. AB, you can always write it as A union AB. Like now, this is Borel set, correct? Because that's the way we have defined. And A, this fellow we have defined. This is already something of Borel sets, but that we have done with respect to this definition. So somehow I have to express A in this way. So um, no, I think it's better. No, I think we go by this technique because there will be a problem here. It has to be, it has to done more delicate, but this definition, this is fine. I mean, this is fine. So, so this is the way you consider R and and Borel sigma algebra over R, and then we have to, yeah. So there are certain things like so you have. So what we have done here till now, we have considered capital omega and considered the set of sigma, I mean, the sigma field over it. Okay. And now we'll introduce the probability measure here. So because, I mean, this is my sample space, right? I mean, capital omega is my sample space, correct? Is capital omega is the set of all possible outcomes, and that is called the sample space. Correct. Mhm. So, so it is the set of all possible outcomes of an experiment, or this is called the sample space. Okay. This is called the sample space, the set of all possible outcomes of an experiment. And, so capital omega is the set of all possible outcomes of an experiment. And and you consider the F, you consider the F, the the sigma algebra over sigma algebra over capital omega. So so in a sense that you consider the collection of subsets. So F is the collection of subsets over capital omega, which satisfy those three properties, right? Which satisfy those three properties. So you have a sample space and you consider collection of subsets of over omega, that is the sigma algebra. Okay, so this is your sigma algebra. And any element A of F, this is called the event. Any element of this thing is called event, and we will assign the probability over an event. So we will do this next time. Okay, ठीक है? Hello.
Yes, sir.
Yeah, so we'll do about we'll introduce the probability measure in the next class. Okay, ठीक है?
Okay, sir.
Okay, bye.
Bye, sir. Thank you, sir.